All right, how's it going, everybody? We are here for our second video of week 10. We're going to look at section 3.2, where I'm making this video here today on March 30th here. So today we're going to look at section 3.2, straight line solutions. And this is very, very much going to build off of yesterday's video here. We're going to look at that same example from yesterday's, or from the previous video for this week, for most of today. What our goal is here today is to figure out how we can avoid doing calculus at all to come up with general solutions to our systems of linear differential equations, by doing a little bit of linear algebra rather than doing a little bit of calculus. So in the last video, what we saw was that for systems of linear differential equations, the linearity principle is going to allow us to construct a general solution to the system by taking linear combinations of any two solutions, as long as those two solutions are linearly independent of one another, meaning that one isn't just a constant multiple of the other. So this means that our goal should be to find the easiest two linearly independent solutions we can find, because if we have those two, then all linear combinations, all sums and differences of constant multiples of those two will produce all other solutions. Further, in the example in the previous video, the two solutions that we were using to construct our general solution were actually straight line solutions. Now that was something that was sort of specially picked out by the book, but that we're going to kind of hunt for today. All right. Because that's really nice, right? I mean, if I were to say to you, hey, we need to come up with, identify some curves in the plane here. I mean, I'm hoping that you're all hoping that they're straight lines. It's the easiest curves that there are out there. So it's really nice. So it's going to be the case that we're going to see over the next couple sections that not all of our systems of linear differential equations are going to have straight line solutions, but it would be sure nice to find them when they do exist. It's also the case that for those that don't have straight line solutions, they sort of do, just in a different sense. They're not actually going to get graphed as a straight line solution, but all of our math is going to be exactly the same. And I mean, the special magic word is directly above my finger right up there, complex. We're going to look at some imaginary valued solutions here. And we're going to realize that those are, in a sense, representing the equivalent of our straight line solutions. It's just that when imaginary numbers get involved, the lines aren't straight anymore. We'll get to that in their second video next week. So what we want to do is we want to revisit our example from the previous video to see what we can expect to have happen today. So in our previous video's example here, we were given this differential equation. And remember that what this really represents is dx dt being 2x plus 3y, and dy dt, it looks like, is just negative 4y. We have our A matrix here is just that 2, 3, 0, negative 4. That's our coefficient matrix. And so this is our way of representing a system of differential equations in matrix vector form right there. What we found is that, and so a bunch of notation on the screen, but stop and realize that this is just me putting vertical vector things for things that you normally see side by side. They're just vertically stacked on each other here. So the first initial condition that was originally given, and this was back in chapter 2, was that at time 0, our x value is 1 and our y value is 0. And this gave us our first solution where, and again, these are x and y values and just in vector format right there, it gave us the solution that y could be equal to 0. And notice that if y is equal to 0, dy dt is just 0. If y is equal to 0, then we just get dx dt equals 2x, which gives the solution e to the 2t. Notice that this vector right here, I could factor out e to the 2t from this vector right here. And by factoring out e to the 2t, I have e to the 2t as a constant sitting out front, times I just factored out e to the 2t from both the top and the bottom part, the x component and the y component, and that just left me with 1, 0. Very, very similarly, we were given a second initial condition here of negative 1, 2 for x and y. This led us to the particular solution that we called the vector y2. It gave us it gave us negative e to the negative 4t and 2e to the negative 4t. Again, I'm noticing that there's really a common factor of e to the negative 4t in both the x and y component. And so if we choose to factor out that e to the negative 4t as a constant out front, then that actually leaves us with the remaining constant vector of just negative 1, 2. So a really important thing to note about these two solutions that we came up with, kind of like these parts right here at the end, is that as t varies, the solution itself is always a constant multiple of its initial condition. Our initial condition here was negative 1, 2, and this is a constant multiple, e to the negative 4t, of negative 1, 2. Now, what that constant is, e to the negative 4t, does change as t changes out there, but our solution seems to just be some constant multiple of the original initial condition, meaning it's going to be on some location on that straight line, right? We're just doing a vector times a constant. It's just going to be a longer version of the vector. So that says to me scalar multiples of vectors always, or excuse me, that doesn't say to me. This is just a general truth about how vectors work. Scalar multiples of vectors always lie on the same line, the ray through the origin, as the original did, right? So again, the point negative 1, 2 is on some negatively sloped line, and it seems that what we're getting is our solution curve here associated with that initial condition is always just a constant multiple of negative 1, 2, meaning it's always on this straight line that is going through the origin right there. This is kind of how I can see that we're getting straight line solutions, that we're just getting multiples, e to the negative 4t, of a single constant vector right there. So we want to kind of generalize this. So to generalize this, I can say, along a straight line solution through the origin, the vector field must be pointing directly towards or directly away from the origin, right? Our straight line solutions, if they're going to pass through the origin where there's an equilibrium there, that means that our slope field must always be pointing, no matter where we are, right? If the origin goes through my arm here, if we're anywhere on this straight line solution, it must be that that underlying slope field that's behind us here must be pointing either directly towards the origin, right? Directly towards it, or if we're right here, it must be pointing exactly away from it because we're still on a straight line. So it could be going towards or away, but in a straight line fashion, right? Now, this is our English sentence up here. I want to kind of think about this mathematically. This says to me, look, if you can find some location x, y, and if you want to show that it is on a straight line solution, then what must be the case is that the slope field at the point x, y must be pointing in the x, y direction, or a constant multiple there, those are really the same direction, right? So again, if we're at some point in space, we either need to be pointing directly towards the origin or exactly away from the origin. And that's going to mean that our vector is just some constant multiple of our location, right? We're going to get sort of the negatives if it's going towards it, and we're going to get the positives if it's moving away from it, or any constant multiple of it. Right. This is the statement that's going to really help us figure out how can we exactly identify where are we if we are on a straight line solution. So what we want to do is let's go ahead and see this in action with this old example. So this is still that same A matrix that we dealt with all of last video right here, 2, 3, 0, negative 4. And we have some generic vector v that I'm going to call xy here. And what we now know is that if this vector v, if this point xy is on a straight line solution, then it must be the case that we kind of want to make a general statement about this, that it must be the case that when we multiply our A matrix times our V vector, that all we're going to get is just a constant multiple of that vector. Right? So what I kind of want to say here is that it must be the case that 2, 3, 0, negative 4 times xy must just really be some constant multiple. I'm going to switch variables. Instead of writing the k, I'm going to write lambda here, of xy. And I want to kind of talk, let me talk about this. I'm going to write a sentence with this right here. Now, what you know is this. When I write things like 2, 3, 0, negative 4 times xy, I'm going to scroll up real quick. What you know is that's really me just saying, how do you compute the slope, dx dt and dy dt? So this on the left-hand side represents the slope at xy. You know that the equal sign is the word is. And this is a constant multiple of xy. All right. So again, when we do our coefficient matrix A times an arbitrary vector xy, what we're really doing is we're just evaluating dx dt on the top and dy dt on the bottom, our rates of change of x and y. That's giving us what slope, what direction we're moving in the phase plane. It's exactly telling us what our vector looks like in that vector field that's underneath right there. So again, the left-hand side of this is our calculation of the slope at xy. The right-hand side says it should be a constant multiple of xy. So what I'm going to do is I'm going to write this a little bit more compactly. I know that this matrix right here of coefficients, that's what we called A. We define this generic vector xy to just be v. Should be equal to the constant multiple, unknown, of lambda. I don't know what it is. It's just some constant number times that vector v right there. Right? AV equals lambda v. And kind of what we are going to see here is, as I suggested a moment ago, we're either moving directly towards the origin or directly away from the origin. If we are moving towards the origin, then our xy values are going to get smaller and smaller, and so we're going to expect to see negative values for this variable lambda. This is like our decay term. And if lambda is positive, then we are going to point away from origin. Now, what I want to be able to do is do a little bit of math with this statement that's right here, because what I would really like to be able to do is determine, like, what is this vector? I want to know what is the vector that represents our straight line solution, because remember, if I can come up with that straight line solution, and if I can go to those straight line solutions, then we have our general solution to the system overall, which otherwise we can't directly get at just doing calculus here. All right. So what I'm going to do is I'm going to do a little bit of vector math right here. And remember, A is a whole matrix. V is a vector right here. And one very, very important feature of doing vector operations is that the sidedness matters. Right? If I were to rewrite, right, we don't get like commutativity here. If I were to write this as V times A, instead of A times V, that's actually going to be an undefined operation because we're going to have a 2 by 1 times a 2 by 2, and we don't have their inner dimensions matching right there. So it matters that we maintain our order here. So I'm going to do a little bit of modification of this, and I'm going to say, well, one thing I could do if I wanted to try and find the vectors or the constant that's going to make this kind of identify where those straight line solutions are going to be. I'm going to subtract over the lambda v. And now I'm going to recognize that there's that vector v in both terms on that side. And so again, what I'm going to do here, I'm going to do something really important here. One, I'm going to factor out that v. But it's very important here that this v is being multiplied as the right-hand factor here, because multiplication is not commutative for matrices and vectors. So I need to keep the vector v on the right-hand side. The other thing here is that A is a whole matrix, whereas lambda is just a constant number. It doesn't really make sense to me to say take a matrix and subtract 6 from it. So instead, what we typically write here is that this is the constant lambda times whatever our identity matrix is here. So in our case, since we're talking about 2 by 2 matrices, the identity matrix is 1, 0, 0, 1. That's going to say when you multiply by it, if you multiply any 2 by 2 matrix by this identity matrix, you'll get back the exact same original matrix. This is like the matrix version of multiply by 1. It doesn't change the value here. And we've factored out this vector v right there. And so now I have like an alternate way of actually writing that original expression here, right? So what I'm seeing here is that this is really like our 2, 3, 0, negative 4 minus the constant lambda times my identity matrix. So that's really going to be lambda 0, 0, lambda, all times v should be equal to 0. And what that's really going to allow me to rewrite this as is this. I'm going to do the matrix subtraction here. So I'm going to get 2 minus lambda, 3 minus 0 is just 3, 0 minus 0 is just 0, and negative 4 minus lambda is what we get in our last slot down there. This is times that xy, that's our v vector right there, and this should be equal to 0, 0. I guess technically speaking right here, this is the 0 vector because we're doing matrix operations right there. That's kind of trivial right there. So what did we say about this last video? Well, what we said last video is that when we're ever in this solving scenario right here, this system of equations right here will have non-trivial results when the determinant of this matrix is equal to 0. So what I'm going to do is I'm going to set the determinant of this matrix equal to 0 and solve, and we're going to see that we're going to be able to identify what are the values of lambda that are going to make this a true statement right here. So I'm going to do my determinant of a minus lambda I is going to be the determinant of this matrix, 2 minus lambda, 3, 0, negative 4 minus lambda. And I want this to be equal to 0 so that I can arrive at some non-trivial solutions. Whatever values of lambda make this equal to 0 is going to give us the non-trivial solution, the one that we're actually hunting for here. So remember, to find our determinant, we do our, as I verbalize it in my head, the downs minus the ups. So my downs here look like 2 minus lambda times negative 4 minus lambda. That's the product of the down diagonals minus the product of the up diagonals. Well, that just actually went to 0, and I'm going to set that equal to 0. So I'm going to do something here, and by the way, I'm going to do it right now, right away on the first one, because I do this with all these guys here. We're going to see this matrix setup like 100 times over the course of chapter 3 here, and every single time you're going to have this, your variable that we're actually interested in solving for as sort of the second term in a factor right here, and I'm always thinking to myself, just like my quadratic stuff, I like things like x minus 2, x minus 5, instead of like 5 minus x and 2 minus x, stuff like that. So what I'm going to do here is I'm going to factor out a negative from this term, and I'm going to factor out a negative from this term, which allows me to write this a little bit more nicely as lambda minus 2, lambda plus 4. And notice, by factoring out a negative from both, those negatives really just canceled. And so this is, and this term was 0 right there, so that's equal to 0. And so it looks like we're arriving at lambda equals 2 and negative 4. So what the heck does that mean to us right here? Well, it looks like what we've done is we've found that if we use the constant multiple of lambda being 2 or of negative 4, then that should lead us to being able to identify what vector this is going to be. So notice here in this AV equals lambda V setting right here, we really only knew A. But we knew that the solution to this system would have non-trivial solutions if the determinant of this ultimate matrix right here would have been equal to 0, the A minus lambda I matrix. And we've determined that that will occur when lambda is equal to 2 and negative 4. So what I'm now suspicious of is that knowing what lambda is, 2 and negative 4, that should lead me to be able to solve for the vector v. The vector v is exactly going to be the vector that's describing what that straight line solution is. That's going to tell us where our straight line solutions exist. And if we can find 2 straight line solutions that are going to be associated with 2 constant multiples right here, then we're going to be able to build our general solution from those things right there. All right. One other thing I'd like to point out to you, just as your little like teaser for 30 minutes from now, where have we already seen 2 and negative 4 crop up in association with this A matrix? 2 and negative 4. Have we seen a 2 and a negative 4 crop up anywhere? We have. All right. We'll be back to that. So now that we know these values of lambda, we can go ahead and find the associated vectors, which must then represent our straight line solutions here. So let's go ahead and do this for each of our lambda values here. And you can see some of these magic words down here at the bottom that you may or may not recognize. If you don't recognize them now, you will. These will come up in every single math class that you ever take after this one right here. That is a promise. So let's go ahead and do this here. What I want to do is I want to return to my A minus lambda I times V equals 0 setting right here. So given that lambda equals negative 4, we're going to do that. We're going to do the same math twice here, right? I've got that my A minus lambda I times V is equal to 0. And in our setting for ourselves right here, A minus lambda I, we now know what lambda is. Lambda is going to be this negative 4, right? So I'm seeing up here, I'm kind of copying my work from up here. There's my A minus lambda I sitting up there at the top. So I'm going to get things like 2 minus negative 4, 3, 0, negative 4 minus negative 4. So this is me plugging in lambda into A minus lambda I. This is going to be times some arbitrary vector. I'm just going to call this UV just because I don't want to create any like variable confusion over here. And this should be equal to 0, but 0 as our appropriately shaped vector right here. So I clearly didn't give myself enough room for our first look at this right here. So what am I seeing? Well, what I'm seeing here is this is 2 plus 4, which is going to give me 6. 3 survives. This is 0. And what do you know? This is negative 4 and positive 4 right there. So that's also going to go to 0. And so it looks like whatever our vector UV is going to be right here, we can now solve for what it must be. Now, here's the really interesting thing about this. Typically, when we solve a system of 2 equations with 2 unknowns, we find a point that is the solution. But notice that when we plugged in our special value of lambda, we now have 2 unknowns uv but only one meaningful equation. The other equation is just 0 equals 0 right here. So instead of getting one point as a solution, we're going to get an entire line of solutions right here. And gosh, maybe I just shouldn't. Okay, I'm gonna swap back. I always write these as UV to avoid variable confusion, but I'm gonna write these as just XY right now so that we can really see that we're getting a line as our answer right now. And so what this is really saying to me is by doing a little bit of matrix multiplication, right? Row 1 times column 1 and adding each of the results is 6 times X plus 3 times Y. Row 1 dot product with column 1 is telling me 6X plus 3y equals 0, because that's my top part right there. Our other equation is lame. It says 0x plus 0y equals 0. Well, that's trivially true for any value of x and y, so that doesn't really help us with anything right there. But this equation is really good right here. If we do a little bit of solving here, then we're going to find that y equals negative 2x is our solution to this equation right here. And this is exactly the straight line solution that we found yesterday. That this was living on the negative 1, positive 2 vector. That's exactly a point that's on this straight line solution right here. Right? And given that lambda equals negative 4 was negative, that says to me solutions. So let's say lambda equals negative 4 says solutions move toward origin. We're decaying towards the origin along y equals negative 2x. And now we can do the exact same math here for lambda equals 2. And let's see what we get here. And by the way, I'm going to want to state this solution right there as a vector instead of as an equation here in a minute, but that's okay. We can do that guy right here. I'm going to kind of come back to that. So again, our same statement right here says a minus lambda I times v equals 0 is going to be rewritten by me as, and again, just these negative 4s that are right here, we're swapping those out for positive 2s now. So now I'm going to get 2 minus 2, 3, 0, negative 4 minus 2 times xy equals 0, 0. Notice in this case now we're getting, it looks like up top I'm getting 0, 3, and 0, 6 times xy equals 0, 0. So this one's a little bit weirder right here. Oh wait, that's going to be a negative 6 down there, but that is going to end up not really mattering to me right here. So the if I write out this stuff right here, it looks like row 1 times column 1 is going to be equal to row 1. Row 2 times column 1 is going to be equal to row 2. So that's going to tell me 0x plus 3y equals 0, which is going to tell me that y equals 0. And notice our other line tells us the same piece of information here. Nothing different, right? This is also going to tell me that y is equal to 0. So it looks like y equals 0 is going to be the line upon which we're going to expect to see solutions grow. Because that lambda is 2, that's going to represent a positive number that is going to indicate growth along that line right there. And so lambda equals 2 says solutions move away from the origin along the straight line y equals 0. All right, so we kind of did it right here. And I want to point out some other really nice things here as well. This equation right here. Now, the statement that I'm making down below is, so what we just found is two eigenvalue eigenvector pairs. These lambdas are going to be our eigenvalues, 2 and negative 4, but we didn't find vectors, we found lines. What I want to write these as is vectors. So one thing I'm noticing here is that, and associated with this equation right here, if our x value was 1, then what must our y value be? Well, we plug in 1 for x, we're going to get negative 2 for y. And it turns out that this is maybe one representative vector of the line y equals negative 2x. All scalar multiples of this vector will get us all the points on that line, y equals negative 2x. So I could have said 2, negative 4. I could have said 3, negative 6. I could have said negative 3, positive 6. That would have just been on the other side of the origin out there. All those are representatives of that line. Very, very similarly, over here you should notice that this guy right here, if I plugged in anything I want for x, like 1, it's always going to give me 0 for y. So this is maybe a representative vector that's associated with the line y equals 0. And now, have you seen these vectors before? 1, negative 2, and 1, 0. Let's see. Have you seen those vectors before? Now, this one's a little bit different. I said 1, negative 2 down there. Here's negative 1, 2. But again, I'm kind of just referring to that as one vector that is representative of all the points on that line, because all scalar multiples of that vector will get us all of the points that are on that line right there. Seems like our eigenvalues and our eigenvectors are actually the key to us building our solution. Eigenvectors, eigenvalues that we're arriving at right there. Very cool. So what we just found are what we refer to as eigenvalue eigenvector pairs. So we just found that lambda 1 equals negative 4 is associated with eigenvector 1, which is going to be our 1, negative 2 vector. And that eigenvalue 2 was 2. And the associated eigenvector that went with it was 1, 0, right? Notice here what we're always asking ourselves, and in both of these cases we ended up with some sort of like triviality in our matrix multiplication, right? This entire equation meant nothing right there, the 0x plus 0y equals 0. Down here we had two equations, but they both led us to the same line of a solution. Having both those equations didn't help. They both were essentially equivalent to one another, right? So there's some triviality in these matrix operations that were right here. So notice that what our job really is going to be is not so much to state an equation like y equals negative 2x and y equals 0, but rather to suggest what is the simplest possible vector I could choose for xy to make this overall true. And I'm noticing here that if I let x be 1, then I get 6, and then I need to decide what y needs to be so that its multiplication with 3 cancels out 6. So I wanted y to be negative 2, so that 3 times negative 2 is negative 6, and that led us to the 0, which will always be our vector that's on the right-hand side over here. So this is one of those things where I gloss over this super quickly because in my head, I can just look at this and say to myself, if xy is 1, negative 2, this is going to be true. And all I'm trying to do is make all of our terms here cancel and go to 0, which will always be the right-hand side of our equations in this type of setting here. Very similarly over here, I'm saying to myself, well, it looks like x can be anything it wants because it's going to get multiplied by 0. As long as y is equal to 0 times 3, then adding those two parts together, we're always guaranteed to get 0. So that's what would lead me to say 1, 0 is the appropriate vector to multiply this matrix by, to get 0 out on the right-hand side over there. So these vectors are going to be the representatives of these lines that they're living on. Any constant multiple of these vectors will get you to any point on these two lines right here. So graphically, I like to think of the line, but to do the math, it's more helpful for me to state the vector, and you can clearly see that that's going to be our useful way for us stating our solutions to the differential equation as well. All right, so again, I made a promise to you 1 second ago, which is that if you don't recognize these words, you will. My like story for this is one of those things in math where eigenvalue, eigenvector stuff comes up so often that when people say to me, hey Tony, can you tell me what an eigenvalue and eigenvector is? I really can't, because they are so everywhere in math that they do like a million jobs for us in a million places of being these like representative ideas about things. Eigen is a German word that means own or self, not like the verb, but like yourself. And so what an eigenvalue and an eigenvector are really trying to describe is like, what is like a characteristic, like if I were just to come up with one number that helped me describe this whole system of differential equations, what would it be? In fact, in this case, we need two numbers because it's a 2 by 2 matrix here. But this is sort of like boiling down everything to being one characteristic value that's helping us describe behavior associated with this. We're obviously losing information when we take a whole matrix and try and condense it down to one representative number. But my stupid story that's my answer to people when they ask me really generic questions about eigenvalues, eigenvectors is there were 2 different times when I was in grad school where I was taking 3 classes in a given semester. So 2 separate semesters, 3 classes in each of those 2 semesters, where in 1 week of class, we were discussing eigenvalues and eigenvectors in all 3 classes at the same time, and that happened to me twice, right? These are a cornerstone of like every topic of math that ever comes up. You will never escape discussion of eigenvalues and eigenvectors in like any higher level math. It always comes up to be some key representation of what's going on. This type of equation right here that you're seeing, where we start with a matrix times a vector equals a constant times that same vector being rewritten as a minus lambda I times v. This type of stuff, this stuff that you're seeing on the page right here, this will crop up in like 90% of all the math classes you're probably going to take from now on. It just keeps on being a very relevant feature of a lot of things here to compute these like sort of characteristic values of interest for us here. All right. Let's see, where am I at right here? I get so worked up about this. So in general, given a matrix A, the scalar lambda is an eigenvalue if there exists a non-zero vector v, xy, such that AV equals lambda v right here. And all I'm really trying to say here is, you should notice that this means that multiplying the matrix A by a vector is the same as multiplying a constant of lambda times a vector. So it's sort of like a constant, one number, is doing the same job as an entire matrix right here. So that's what I like to, when I like to say that, like philosophically speaking, an eigenvalue is supposed to sort of be like a one number representative of an entire matrix action. That's kind of what I mean right here. Multiplying by that one number lambda does the same job on a special vector as multiplying by the entire matrix would end up doing right there. So let's see some more examples of this, kind of help ourselves really understand this definition of eigenvalue, eigenvector, and in what way it's special and in what way it's unique. And let's do a little bit of math right here to do this. So our brief little linear algebra exercise here, given that the matrix A is, and by the way, I had some typos earlier as I was going through my notes here. I think this is what I want. 4, 3, negative 1, 0. So a different A matrix here now, different than the one that we had before. Given that this is our coefficient matrix A, check to see if each of these three do represent an eigenvector or not. If this does turn out to be an eigenvector, then find the associated eigenvalue. Notice that this is backwards of the way that we just did a second ago. A second ago, we found our eigenvalues first, used them to find the associated eigenvectors. Here I'm proposing to you potential eigenvectors, saying, is it one? If so, what's lambda? So let's go ahead and see what we're looking at here. So my key to this is to remember that our definition here is that AV equals lambda V, right? So I've been given the A matrix. I've been proposed vectors to use for V, and I want to see if I can decide if this relationship holds or not. This is the relationship that defines eigenvalue, eigenvector relationship right here. So what I'm going to do is I'm going to set this multiplication up. 4, 3, negative 1, 0 times 6, negative 2. And the question is, could this possibly be equal to a constant multiple of 6, negative 2? So let's go ahead and do the matrix multiplication here. So I'm still on the left-hand side of this equal sign. I haven't gotten to the lambda part yet. I'm just evaluating my left-hand side right here. So I'm going to get 4 times 6 plus 3 times negative 2. That's my top. On the bottom, row times column is negative 1 times 6 plus 0 times negative 2. That's going to give me 24 minus 6 and negative 6 plus 0, which is 18 and negative 6. The question is this equal to some constant multiple of the original proposed vector? And it looks like the answer here is yes. It looks like if lambda were 3, then this is a true statement right here. So since I was able to find a constant lambda that made this statement true, that means that this vector and this eigenvalue, this lambda, represent an eigenvalue eigenvector pair associated with this particular matrix. So we get to say yes with lambda equal to 3. Let's do it again. Is the vector 2, 3 an eigenvector associated with this matrix? So again, this is your matrix multiplication practice right here. And again, you're going to do so much matrix math this chapter. None of it's going to be harder than this. but you're going to do so much of this that you need to be good at this, and you should probably be able to do this in your head right here. So this is our practice to get good at this right here. So again, all of this is my left-hand side of the computation right here. I'm just going to indicate this right here. This is my AV equals lambda V. All right. So same thing here. So what we're getting here is this should be 4 times 2, which is 8, plus 3 times 3, which is 9. Negative 1 times 2 is negative 2, plus 0. So we're just getting negative 2 plus 0 down there. So this is going to be 17, and negative 2 is my result for the left-hand side. And the question is this equal to some constant multiple of 2, 3? And it looks like the answer is no. And I know the answer is no because lambda would have to be 17 halves to make the top work out, but 17 halves doesn't make the bottom work out. So we're going to say here, no. There's no value of lambda that would make this a true statement given that A and that V. Therefore, this V cannot possibly be an eigenvector of this matrix. Let's go ahead and do our last example here. 4, 3, negative 1, 0. We're wondering if negative 1, 1 could possibly be an eigenvector associated with this matrix right here, a coefficient matrix. So again, trying to do this a little bit quicker in my head. 4 times negative 1 is negative 4. 3 times 1 is positive 3. Negative 1 times negative 1 is positive 1. 0 times 1 is 0. This is going to give me negative 1, 1. And the question is this equal to a constant multiple of negative 1, 1? Well, obviously yes, with lambda being equal to 1. Right? So it's pretty easy for us to test if a vector is an eigenvector of a matrix, or if it's just some generic vector that's not anything special relative to that matrix. If it is an eigenvector, the deal with these is that eigenvector eigenvalue pairs, it's almost always the case in math that it's never really valuable for you to know an eigenvector without its eigenvector, and vice versa. These are really like a pair of information that go together right here. And that makes sense because they're defined as a pair, right? This AV equals lambda V, that's one equation using two special things, lambda and V, the eigenvalue, the eigenvector. So they're really like kind of jointly defined. And so it often ends up being the case that we jointly care about identifying them here. So we should note real quick that being an eigenvector is definitely a special property. Most vectors are not eigenvectors. This matrix here only has two distinct eigenvectors, and I gave you both of them right here. All other vectors that we'd try, so given my next sentence right here, wouldn't work out. Now, the other deal though is that eigenvectors are not unique. All scalar multiples of an eigenvector also an eigenvector. So if I were to ask you, is 12 negative 4 an eigenvector here? The answer is also going to be yes. It's just that our lambda, actually no, our lambda should end up remaining the same right there, I believe. So the point here is any eigenvector, any scalar multiple of an eigenvector, also an eigenvector representing essentially the same piece of information. So up here when I said choose the simplest vector that would make this true, if you were to come up with 2, negative 4 for this guy in purple right here, you'd be equally correct. There'd be nothing wrong with you stating that as your answer right there. So all scalar multiples of an eigenvector are also an eigenvector, and we can see this by doing just a real brief little bit of math right here. If I have a constant multiple of my eigenvector, so this is my constant multiple of my eigenvector, then according to our matrix operations here, constant multiples can be factored out from these operations right here. So I can write this as k times AV. What I know that AV is equal to is lambda V. And I can just swap the order of multiples of constant multiples right there to write this as lambda times kv right there. So it looks like we're getting that a kv equals lambda kv, in which case we're seeing that kv is an eigenvector. So that just says any constant multiple of an eigenvector is also an eigenvector right there. So this is good. So they are very special, but in a sense there's an infinite number of them, but they're always just going to define for us one line. All constant multiples of one vector are going to get us all of the locations on a straight line through the origin, since that's where our vectors are going to be starting from right there. So this is our way of saying this is actually defining for us an entire line, not just one vector taking us to one point, because we get all scalar multiples are also representative of the same eigenvector right there. So let's kind of group up now all of our eigen discussion that we've had here so far. So what we've seen is that to find eigenvalues of A, we want to find a lambda, in general, to find eigenvalues of a general A matrix here, then all we really want to do is do the determinant of A minus lambda I and set that guy equal to 0 to find our non-trivial solutions. So for a general matrix, for a general A, for a general coefficient matrix, A equals A, B, C, D, we're going to get that the determinant of A minus lambda 0, nope, that's B, and this is going to lead us to the statement A minus lambda. So our determinant here is the down diagonal minus the up diagonal. My typical thing to do with this, again, as I kind of have already said to you guys, is we are going to end up with this type of expression so many times here that notice that if we factor out a negative from both the first factor and the second factor, then each of those negatives cancel, effectively allowing us to like switch the way that we've written these without actually meaningfully impacting the statement that we're looking at right here. And so in general, then we're going to get that lambda minus A, lambda minus D, minus BC is equal to 0. And if we multiply this out, we're going to get a lambda squared. We're going to get a, let's see, minus A plus D lambda. We're going to get an AD minus BC is going to be equal to 0. So this should sort of, so what this is referred to as, this is the characteristic polynomial. All right, so here's an important definition for us. The book will reference the characteristic polynomial of a matrix many times. The characteristic polynomial is the resulting polynomial from a performing your operation of taking the determinant of your coefficient matrix A minus the identity matrix times lambda and setting that all equal to 0 and attempting to get into a solving scenario here. Since we're only talking 2 by 2 matrices in this chapter, we're always going to get quadratics out on the other end. You should notice that there are two terms of interest to us right here that we're going to get for our coefficients. AD minus BC, this is the determinant of A. And A plus D, well, you should notice that A plus D, that's really the sum of the what's referred to as the main diagonal right here. This also has a special name in linear algebra right here. I'm going to say it right now because it's going to come up in like 3 weeks. Don't worry about this name at all right now. But this is what we refer to as the trace of A. But we'll come back to talk about this a little bit more later. But the point is, the two coefficients that crop out in our characteristic polynomial every time are two like already defined quantities in linear algebra. So that's also cool to see that there's maybe some more like deep ties to linear algebra happening right here. The trace and the determinant of our original matrix are the coefficients in our linear and our constant term associated with the quadratic characteristic polynomial that we're always going to see from our A matrices here. Now, to compute our eigenvectors, we return to our definition of eigenvalue, eigenvector stuff right here. And so the definition for us is that AV equals lambda V. And that's always going to lead us to a statement that looks like ABCD times XY equals lambda times xy, or which we might write as ax plus by dx plus cy equals lambda x, lambda y. And if we can solve this equation for x, y, then we have found the eigenvector. And that's exactly what we already did up there above. This looks a little bit different because we're in general form, but that's exactly what we did right here, right? We had our matrix right here times xy. It was equal to some other vector that we had right there, and we set this guy equal to 0, and we solved, right? So this is our same exact setup right there. I just didn't have the subtraction included in the way that I wrote it right here, where this was subtracted on over to the other side. So let's go ahead and see if we can kind of follow this process right here and see if we can figure out what our general solution should look like here. Then we'll finally relate this all, or sorry, not our general solution, but maybe our graph. And then we'll bring this all back together to get our general solutions right here. So let's go ahead and find the eigenvalues and eigenvectors associated with this given matrix, 2, 2, 1, 3 right here. So let's kind of do all the math that we've seen here today. So what I'm always going to end up doing here is I am interested in setting the determinant of a minus lambda I to be equal to 0. This is going to help us find the value of lambda that's going to help us find the vectors. The vectors are going to be representative of our straight line solutions, so they're going to inform me where I can draw some straight lines on my final solution graph. In our case here, this means that we're interested in the determinant of 2 minus lambda, 2, 1, 3 minus lambda, and setting that equal to 0. So therefore, we're going to get 2 minus lambda, 3 minus lambda. This is my determinant computation, minus 1 times 2 is equal to 0. I usually don't write that previous line that way. I always jump to having kind of, in a sense, factored that out right there. So what? Lambda squared minus 5 lambda plus 6 minus 2 equals 0. Lambda squared minus 5 lambda plus 4 equals 0. And so what? Lambda minus 1 lambda minus 4 equals 0. And so it looks like we found lambda equals 1 and 4. So I found my two eigenvalues. What I'm now interested in identifying is what are the associated eigenvectors that go along with these guys. So now let's go ahead and find their eigenvectors. So one by one, we're going to come back to our AV equals lambda V equation here, right? So what I'm interested in doing now is saying, our A minus lambda I V equals 0. So for lambda being equal to 1, what that says to me is, so notice here, this is our A minus lambda I right there. So it's really like I'm just plugging in 1 into this, this matrix that we've got right here. So it looks like I'm going to be getting 2 minus 1, 2, 1, 3 minus 1. This times some vector that we're interested in, xy, it should be equal to our 0, 0 vector. A little simplification is going to show me this is 1, 2, 1, 2. xy is equal to 0, 0. All right, and notice, once again, and this should happen every time. If this doesn't happen, you did something wrong. This is a system of two equations, but where the second equation provides you no new information relative to the first. This is going to give us an entire line of solutions rather than just one point of an intersection of two distinct lines out there. It's always going to happen this way. So this is where I'm thinking to myself, okay, what could I choose for xy? Since we're going to get an entire line of solutions, there's an infinite number of things I could say for xy right here. So I'm going to say v1 is our choice of xy. And what can I do right here? So I'm noticing here this. It looks like, for example, I'm going to get things like 1x plus 2y needs to be equal to 0. So I always like to think to myself, especially when these are the same sign, I'm looking for them to cancel so that I can get 0 on the other side. So I need 1 to be positive and 1 to be negative. So I'm thinking to myself things like, if I let x be 2, then 2 times 1 gives me 2. And now I just need a negative 2 to cancel with it to get to 0. So if y is negative 1, then that's going to work out perfectly because negative 1 times 2 would give me negative 2. So I'm thinking to myself, 2, negative 1 is a good eigenvector for me right here. Because if I plug in 2, negative 1 for xy, we're going to get 2 minus 2 equals 0, and we're going to be correct. Again, it could be that I choose to make this 1, negative 1 half, or negative 1, positive 1 half, or 20, -10. All those would be correct because they're all scalar multiples. So all you ever have to do is come up with any number set pair of numbers that work for xy here, and that can be representative of your eigenvector. It's very, very typical that we really like at least one of the two numbers to be 1 if at all possible, but maybe not use fractions out there. I kind of go back and forth on what I think like the easiest way for me to phrase these are, but this doesn't have any like terrible numbers in it right here. I'm pretty happy with that as my eigenvector right there. So let's do the same thing here for lambda equals 4. In this case right here, I'm going to do my a minus lambda I. So I'm just kind of mimicking our structure right here. So I'm going to get a 2 minus 4, a 2, a 1, and a 3 minus 4. I'm going to simplify a little bit, and I'm going to see that this is leading me to -2, 2, and 1, -1, xy equals 0, 0. Now, again, you should notice that this second whole line down here is just a constant multiple of the first line right here. You multiply this whole line by -2, and you've got the whole first line right there, meaning this second equation isn't actually providing us any new information whatsoever. So this is a system of two equations where there's redundancy in there. It's actually the same equation twice, meaning it's just all solutions that are on this given line right here. You should notice that this is like our simplest possible setting because my goal is for these two values to cancel out and be 0, and they're already set up to cancel out. So it looks like if I just make x and y both 1, then we're going to get -2 and +2 equals 0. So I think that an easy choice for my eigenvector here is just 1, 1. Now we found the two eigenvectors that relate to those two eigenvalues. So before I kind of go further with this, what I want to now suggest is these should represent our straight line solutions. So what I'm expecting to see here is along the line that's associated with 1, 1. So notice that the point 1, 1 is right there. The line through the origin that that's associated with is going to be the line like y equals x. Right? So there's one line along, it's a straight line solution, and I'm expecting to see solutions grow away from the origin because of that positive value of lambda. Similarly, along the line tied to 2, -1, so I'm going to go to 2, -1, that's the point that's right there. I'm looking for all constant multiples of it also work, right? So the line that this is describing to me is this line of slope -1/2 passing through the origin here. And I also am going to expect to see my solutions grow outwards along this guy right here. It looks to me, just based on these two straight lines right here, like a reasonable description of the equilibrium at the origin might be that it's a source. It seems to me like all the curves that I can see so far moving away from it, my curves so far are just straight lines, are all moving away from it, right? So this is sort of like a source type behavior right here. Now, one of the slightly tricky things here is what do the rest of our curves out in space look like? A little bit tough to, there's a slightly difficult judgment to make in association with these that we're going to talk about a little bit more in 3.3 next week. But I'm expecting to see some curves that are also moving away. And so I'm going to expect to see some things that look like this. But you should ask yourself right now, is there some other way that you could be drawing this that you think might also work out right here? And why or why not is it yours versus mine? I do want to go stop and graph this guy right now using technology to verify that we're doing this correctly. Um, So let's go ahead and look at this guy over at Bluffton and see that we're going to get a graph that does, in fact, look like this guy right here. So heading over to Hey, we got audio again. Okay, cool. So now I'm over here. Let's go on over to Bluffton. Let's go ahead and throw in our system that we are working with right here. We were looking at, and to kind of return to our example briefly here, our example has 2, 2, 1, 3. That means that our equations are 2x plus 2y and 1x plus 3y. That's what I got to throw in here. So we're looking at 2x plus 2y and 1x plus 3y. Right? I know I've learned now I'm always going to go to Runga cut of 4 and change this to 0.01 at least. And I'm going to go ahead and kind of like hit enter here, right? Is it graph these guys right here? Um, Yeah, so I'm seeing my slope field that's out here. Before I go and do any clicking around out here, I'm going to throw in exactly those vectors that we had identified there. All right, so coming back over here, we found 2 as the x value and -1 as the y value. Let's see if this really is a straight line solution. Hey, there's a nice straight line right there. And in fact, maybe what I should do is do like point 0.2 and point 0.1 to get one that's closer to the origin so we can actually see it right there. That's nice. And if I want to see that I'm going to get the same thing on the other side, I'm just going to swap where my negatives are at. Hey, that feels pretty good. The other one that we found was 1, 1. So I'm going to do point 0.1, point 0.1 because any constant multiple should also work. And so let's go ahead and do that. Point 0.1 and point 0.1. Hey, more straight line stuff right here. And similarly, I'm going to get the stuff on the other side of the origin right there. All constant multiples work. I just multiplied by -1 right there. And yeah, we're getting more straight line stuff right there. And it does, in fact, look like all of our other curves are going to do this, leaving the origin. And notice, by the way, all my arrows are pointing in the correct direction. All this stuff is leaving the origin right here. So when I click near the origin, they're all leaving the origin right here. And they're all sort of following our straight line solutions in a sense, right? It seems like they're following this straight line solution really close. And then as time goes on, it looks like they're more mimicking our other straight line solutions. We're going to talk about that a little bit more in 3.3 out there, but this is good. This exactly matches what we just came up with for our eigenvalue, eigenvector information right there. Eigenvalues are telling us growth or decay. Eigenvectors are telling us in which direction, and that's what we just saw right here. And I clicked a whole bunch and cluttered it up, but at least that image was there before I did so. And we verified at least that our straight line solutions were legit, which is really cool. Okay, so relating this now to our solutions, right? So this actually allowed me to do a pretty good job of drawing a graph. But what I'm really interested in, all the way back up at the top up here, is what I'm really interested in is, can I come up with a general solution to my system of differential equations rather than just these particular solutions that are at a point? I can clearly see that my eigenvalues and eigenvectors are playing a massive role in how I write these, but we want to kind of see like our last like bring it all together kind of example that's going on right here. So let's do the bringing it all together. In that overused example, and boy have we overused this example by now, huh? What we had was we were given that dx dt was equal to 2x plus 3y, and dy dt was equal to -4y, right? So this is our partially decoupled system. Technically, we were actually able to solve this by hand because it was only partially decoupled. We could solve for y first, then plug that value in for y, then do the linear integrating factor here for x, and we actually got this solution like a month ago in chapter 2. But now what we've done is we've kind of upgraded to be able to write this as a system. So dy dt equals 2, 3, 0, -4y, the vector y. And this said to us we've got this coefficient matrix A of 2, 3, 0, -4. It had solutions of y1 of t is equal to e to the positive 2t 0 equal to e to the 2t 1 0, and y2 of t equal to negative e to the negative 4t and 2e to the negative 4t, which, if we factored out that e to the negative 4t, gave us negative 1, 2. We also found, sorry, one second. We also found this A matrix has eigenvalues, which I'll abbreviate as evals, of lambda equals 2 and negative 4, associated with eigenvectors, evex, of 1, 0, and negative 1, 2, respectively. Because that order matters. Remember, this isn't just like we've got a bag of 2 eigenvalues and a bag of 2 eigenvectors. Each eigenvalue is tied to an eigenvector. It's a partnership right there. So these don't get mixed up. That ordering that I wrote those in does matter right there. Since we have 2 linearly independent solutions, we could take all linear combinations to get the general solution. So I know that these are linearly independent because these 2 eigenvectors are not linear combinations of one another. If they were, then they would just be representing one eigenvector, because any constant multiple of an eigenvector is also that same, or is a representative of that same eigenvector, right? So it looks like we can get our general solution then as, oops, I don't want that 1 down there anymore. Our general solution is take all linear combinations. So this is going to be to say to me, let's do k1 times y1 of t plus k2 y2 of t, which we're really going to be writing as y of t, equals. It looks like we're getting k1 e to the 2t 1 0 plus k2, I'm like looking at 3 different places at once right now, k2 e to the negative 4t negative 1, 2. And this is a great way for us to write our general solutions here. Remember that the fact that there's a vector in there means that we're really actually describing the x of t solution in the top and the y of t solution in the bottom. And that makes sense because we had x and y as our 2 dependent variables in association with our system here. So alternatively, this could be written instead maybe as k1 times e to the 2t, and then minus k2 e to the negative 4t. That's that's the top parts of all this stuff. The bottom parts is k1 times 0 times e to the 2t, that's just 0. And then over here, 2k2 e to the negative 4t. So that's an alternate way for us to write that same solution that we found right there. And the beauty of all this is, we did a mountain of calculus back in chapter 2 to arrive at these solutions, but today we've done 0 calculus and still arrived at the same solution by recognizing that our general solution just consists of constant multiples k1 and k2, exponential functions with a base of e, with powers of each of our eigenvalues times t, 2 and negative 4 were the eigenvalues, times the associated eigenvectors, which gives us sort of the x and the y components of our solution. So it looks like our general strategy can be determine the coefficient matrix A. So given some system of differential equations, identify the coefficient matrix A. We did that. Use matrix A to identify the eigenvalues lambda 1 and lambda 2. We did that. That's how we got the 2 and negative 4 by taking the determinant of A minus lambda I and setting it equal to 0. Once we knew the eigenvalues lambda 1 and lambda 2, we were able to use them to find the corresponding eigenvectors, v1 and v2. We did that. That gave us the 1, 0 and the negative 1, 2. Then finally, we can construct our general solution. And now this looks kind of gross and terrible, but this is exactly what I have in the box right here. This is linear combinations, meaning sums and differences of constant multiples of the two solutions. Sums and differences, that's handled right there, of constant multiples, that's the k1 and k2, of e to the first eigenvalue times t times the eigenvector plus k2 times e to the second eigenvalue times t times the second eigenvector right there. So it looks like we're able to come up with general solutions to systems of differential equations without doing any calculus. And that's kind of crazy. And so what you're going to see is that in chapter 3, we're going to almost never do calculus except for a couple like easy derivatives. And I'm going to show you when that's going to crop up kind of, well, we're not going to see it till later, but you'll see it a little bit right there. And so this is really like the highlight of chapter 3, is that it turns out that we can solve these, what would otherwise be very complicated calculus scenarios. And by the way, I want to just real quickly state here, we're reusing this example because this is an example where we could solve this thing using calculus because this is only partially decoupled, right? This was a y equation only in terms of y. So we were actually able to solve this one by hand. When we have x's and y's in both equation, we don't have a calculus route to getting the solution, but we've just shown that we can get to the solution without calculus anyway, so it doesn't matter that we don't have a calculus route for these guys in general. This was just a special partially decoupled one so we could do it. If it was a fully coupled system, we don't have calculus we can do to solve it, but we do have linear algebra we can do to solve it. So that's super cool for us right here. So what we want to do now is let's do one kind of whole collective example right now and call it a day, right? So what my goal is now is I'm giving you a second order differential equation, not a system. And what I want you to do is draw the phase portrait for this without using technology. Now that's a huge gap for us to jump right here. So here's what our steps are going to be. Step 1, convert the second order equation into a system of first order equations. From the first order system, determine your A matrix. From the A matrix, compute your eigenvalues. From your eigenvalues, compute your eigenvectors. With the eigenvalues and the eigenvectors, state the general solution and draw the picture. And notice we've done both of these things now. We've stated a general solution from eigenvalues, eigenvectors. We've drawn a picture from eigenvalues, eigenvectors. We're going to be able to do the same thing over here. All right, let's see if we can do like one whole big meaty problem right here. By the way, the reason I'm choosing this as our example, as a second order equation instead of a system just given to you as a system, is because I want to show you a really nice underlying thing that we're going to end up seeing. This won't be covered until like section 3.6, I think, but this is one of those things where you're going to look at that and be like, oh, holy crap, that was really nice. And it is. So section 3.6 is where we're going to see that our second order equations are actually deeply tied to our systems of first order equations, but we're going to see an example of it right now. So let's do this thing here. So step 1, everything we've talked about today is about systems, and this is a second order equation. It's not a system. So let's convert this into a system. So what I'm going to do is I'm going to introduce a new variable. So I'm going to say that the derivative of x with respect to time, right? This is our x prime. Let's just call that v. And by the way, I know that not all of you guys are physicists. I'm not a physicist either, but man, calculus was invented to do physics. Whenever I see rates of change of x, I think that the change of position is velocity and the change in velocity is acceleration. When I see x double prime, this is just screaming acceleration at me. It's the second derivative of position with respect to time. That's acceleration there, right? So you can use whatever variable you want right here. It doesn't have to be v. I just use v because my intuition tells me that this is a velocity term, the derivative of an x value right there. But again, that doesn't matter right there. So I'm just defining this. This is sort of like creating a variable substitution in a sense. dx dt has got to be something. Let's call it v. Well, then what's dv dt? Well, dv dt should be the second derivative of x. And what I can see from our original equation is that this should be equal to, I can solve for x double prime by just subtracting these two terms over to the other side. So negative, well, what just happened there? Negative 7x prime minus 10x is my way to write x double prime right there. So I'm going to write that a little bit smarter over here now. And let's go ahead and write this as dx dt equals v. And dv dt is equal to, now I know what x prime is. X prime is just v. And I want to get these things in the right order. I really like my x component first and my v component second. So I'm actually just going to swap the ordering of these down here and call this negative 10x minus 7v. And what that's going to allow me to do is to write this as dy dt equals. And it looks like our coefficient matrix here is no x's and 1v, negative 10x's, and negative 7v's. All right, so this is my A matrix right here. All right, so I have converted my second order equation into a system of first order equations. I have extracted my A matrix from that system. I'm now ready to go ahead and solve for my eigenvalues. So this A matrix is our defining representative of this system. Notice that this is now a coefficient matrix representing a system of differential equations that's equivalent to a second order differential equation. This is crazy. We're really taking like just massive leaps right now all over the place in an outrageous effort to avoid calculus in a high level calculus class. I think this is just awesome right here. And this hopefully is also telling you the broad lesson, which is that calculus is awesome, linear algebra is more powerful, straight up. We're doing more by doing less by using linear algebra here. We're getting greater results and we're doing easier math. Linear algebra is the most like powerful math that we can really do. I think that's a general thing for you guys to all take with you into your math careers in the future here. So let's go ahead and follow our setup here. Our guide says to us that we should determine the coefficient matrix A. We did that. Let's go ahead and find eigenvalues lambda 1 and lambda 2. And the way that we're going to do that is by saying to find eigenvalues, always going to do this step right here. So in this case right here, what this looks to me like is the determinant of, I'm going to show some extra work here because I know there's some people that are totally on board with this, and I know there's some people that are totally lost with this. The identity matrix times the constant lambda is going to be lambda 0, 0, lambda, because it was 1, 0, 0, 1, and we multiplied it by lambda. And we're going to set this equal to really the vector 0 right there, I guess technically right there. And so we really want here the determinant of 0 minus lambda is negative lambda. 1 minus 0 is 1. Negative 10 minus 0 is negative 10. Negative 7 minus lambda, that's just negative 7 minus lambda. And I want this to be equal to, oh, sorry, never mind. This isn't the vector 0, 0 over here because we're taking a determinant. So the determinant's just going to produce one number. So this actually straight up is just 0 right there. It's in the eigenvector part where I want to call that thing 0. That's okay. So let's go ahead and compute the determinant. Remember that the determinant is the product of the down diagonal minus the product of the up diagonal here. I'm going to go ahead and do my factoring out of my negatives in my first step right here. So I'm going to just get positive lambda times lambda plus 7. You should notice that that's me factoring out a negative from the first and factoring out a negative from the second, letting those negatives both cancel, and then swapping the orders because that's the way I really like to write things, minus negative 10, because negative 10 is the product of the up diagonal right there. So it's always AD minus BC, A times D minus B times C. And we want to set this guy equal to 0. And so I'm going to multiply this out, and I'm going to get lambda squared plus 7 lambda plus 10 is equal to 0. This is my characteristic polynomial. And what I want to ask you is, do you recognize this quadratic that we're looking at right now? Lambda squared plus 7 lambda plus 10 equals 0. And my question to you is, do you recognize that structure? It seems like there is some very close relationship between the characteristic polynomial of our coefficient matrix of a system of differential equations and a second order differential equation from which it came. I can't get these both in the same, oh wait, I can get these both in the screen at the same time. Just take a moment and stare at those and say, oh my gosh. And what you should be concluding by looking at the very bottom of the page and the very top of the page is, man, I think section 3.6 is going to be easy. And you're kind of right. Because by the time we get to 3.6, you're going to be so good with your eigenvalues, eigenvectors anyway, And look at how deeply closely our characteristic polynomial is to our second order differential equation. That's always going to work out that way. That's really, really, really nice. So in section 3.6, you are going to skip writing all of this stuff. And the first line of work that you're going to write is going to be the very bottom of the screen down here, because that's what we're getting from this guy right here. That's really, 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 really nice right there. Now, until section 3.6, you are obligated to show me all these steps right here to prove to me that you know why that's going to be the case. But in section 3.6, we're going to sort of formalize this relationship that we're seeing right here. So what are we getting for our eigenvalues right here? It looks like I can factor this guy pretty easily. And by the way, the ones that we've done today have been factorable easily. You're going to get some that aren't factorable. Expect to use the quadratic formula about 30 times in this chapter. It's just going to keep on coming up, and you're going to keep using it. And so it looks to me like our eigenvalues are lambda equals -2 and lambda equals -5. So now that we've got our two eigenvalues, we would like to use those. Coming back up to our instruction set here, let's use the eigenvalues and the definition of the eigenvector relationship to find the associated eigenvectors. So to find eigenvectors, so I'm going to set up this statement right here for each of our lambdas that we're looking at here, right? So lambda equals -2 is going to tell me that I would like to do, and I gotta remind myself of my A matrix. And by the way, here it is. Here's our A minus lambda I. I'm just going to write this right here just so I can see it. This is my... So I'm just kind of reusing my old work. This is the A minus lambda I matrix right there. A minus lambda I is what I'm interested in multiplying by my unknown eigenvector V and setting it equal to, and it turns out that one will be the vector 0 right there. So I'm just slotting in -2 right here into the slots that are right up here. So it looks like what we're getting is +2, 1, -10, and if lambda is -2, then that's -5 right there, times the unknown eigenvector. Actually, it is xv based on the variables that we've chosen. That was a typo on my part, but a correct typo, interestingly enough. Should be equal to 0, 0. I'm just following our definition of eigenvalue, eigenvector statement. Knowing A and knowing lambda, we should be able to solve for V. Once again, I know that I'm on the right track because this is a set of redundant equations right here. If you multiply the top equation by -5, you get the bottom equation. So these are not providing new information by having both of them. My statement that I'm always asking myself is, what's the simplest choice I could make for X and V? And so again, I know that since these are redundant, I only have to deal with the easier of the two. So I'm only looking at 2, 1. I'm never looking at -10, -5. It's providing me the same information as this one is, just with more complicated numbers, right? So what I'm asking myself is, what's the simplest choice I could make for X and V? That would make this true. And we've actually already seen this one. I think that I'm going to let X be 1, so we get 1 copy of 2. And that means that we're going to need -2 copies of 1 to cancel that to get to 0. So I'm thinking that 1, -2 is going to be a good choice for my V1 vector right there. All right. Notice that you can multiply this out if you want, and you can get to the equation like 2x plus v equals 0. That's going to tell you that v equals -2x. And from this guy, maybe you can then arrive at like, if x is equal to 1, then v is equal to -2. And that's how I'm getting my eigenvector right there. And again, this is something where I always notice that every semester, like a third of my students are doing this in their head faster than me. A third of my students are like, oh, I see how you're getting there, and I need to write this equation to get myself there. And a third of my students are like, oh my God, what are you doing? I have no idea what's happening right now. Be aware that all three camps exist for sure. Every time I've taught this class, it's been like evenly split thirds of the this is easy, or I can do this, or I have no idea what's going on. You're going to do this so many times this chapter that I would encourage all of you, regardless of the level of comfortability that you're at, to try and do this by the just look at it method right here, because this really is just solving a tiny system of linear equations, finding a value that lands on a given line. see what's going on here, write as much as you need to, write out the matrix multiplication to get your equations, pick a value for x. And notice, like, since all constant multiples work, there's an infinite number of xv values that work here. Any one of them is correct. It's not like there's one right one and one wrong one. I just very often like to have one of my two numbers be positive one if possible. And it's always possible, but it might make the other number gross, so then I avoid it. Like, in any event, we'll see more examples where I waffle around on what I'd like these to be, but it doesn't really matter. So let's do this again right here with lambda equals -5. Again, I'm just copying from my A minus lambda matrix, A minus lambda I matrix up there. Lambda is -5, so we're going to get a +5, a +1. I'm going to get a -10. And if lambda is -5, well, I'm going to get a -2 down here. Once again, I know I'm on the right track because these are two redundant equations. This is the equation 5x plus v equals 0. This is the equation -10x minus 2v equals 0. But if you multiply the top equation by -2, you get the bottom equation. So it's just a rewritten version. This is just two lines that are on top of each other. So we're getting an entire line's worth of solutions, and we just need to pick out one point on that line as our representative line of that line. One vector that would take us to one point on that line from the origin, and we're good to go. All right, so again, I'm going to think to myself over here, man, I really kind of like to pick things where one of my values is 1. So I'm thinking if I let x be 1, then that's one copy of 5. Therefore, I need -5 copies of 1 to cancel that out. So it feels to me like 1 -5 is going to be a suitable choice here for V2. If you want, you can go ahead and write out the matrix multiplication associated with this line, which would tell me 5x plus v equals 0. And so v equals -5x. And therefore, you could then say to yourself, okay, pick any ordered pair that satisfies this. Well, if x is 1, then v is -5. And that's exactly what I've selected for myself right there. I just did the mental math version of it instead of the write out an equation version of it. So we're good. We're basically almost done here, right? We've done all the heavy lifting here. And again, by the way, this feels probably like a lot to a lot of you, especially if you didn't already take linear algebra, which I don't necessarily expect any of you have. I know that some of you have. This is like literally you're going to be doing this entire page of math in your head in like 2 weeks. I promise. This boils down to be a surprisingly consistent series of operations right here. You'll be surprised at how kind of easy and natural this becomes for you. That's kind of the goal of 3.7 when we summarize all this stuff. So I found lambda 1 and lambda 2. I found v1 and v2. It looks like we're ready to state our general solution and attempt to draw a graph. We're basically there. And we'll just compare a graph with the one technology provides for us, and we're going to call it a day here. So let's go ahead and state our general solution. Our general solution is of the form y of t equals k1 e to the lambda 1 t times our first eigenvector plus k2 e to the second eigenvalue times t times our second eigenvector. And remember, it matters that you keep your eigenvalue eigenvector pairs together. These aren't mix and match here. So we get y of t equals k1 e to the, it looks like I'm just going to call that 1 and 2 for right now. We'll discuss in the next couple sections why we sometimes prefer to order those in a certain order. Referring to things as the dominant eigenvalue is a thing. I'm not worried about that for right now, but it's something we're going to talk about in our coming up sections right here, is ordering those. Right now, as long as the subscripts match, I'm good to go. So -2t times our first eigenvector, which was the 1, -2, plus k2 e to the -5t times our second eigenvector, which was 1, -5. So this is a good final answer right here. I want to rewrite it one way to show you some relationship that's being held in here, and then we'll draw a graph, and then we're done. So I'm doing all the tops first, and then all the bottoms second. So the top says I'm doing my constants first. So k1 is a constant and 1 is a constant. So k1 times 1 is just k1. And k1 is multiplying e to the negative 2t. So I'm going to get a k1 e to the negative 2t. For my other top component here, k2 times 1 is just k2. And so we're getting k2 times e to the negative 5t. Now, what was the relationship that we said x and v had with one another? We defined this whole system by saying the derivative of x is equal to v. So what are we going to get? We better get the derivative of what we just wrote right here, down here, and we will. Negative 2 times k1 times e to the negative 2t is negative 2 k1 e to the negative 2t. Negative 5 times k2 e to the negative 5t. And that totally agrees with the fact that we literally defined v to be dx dt. We literally got the derivative right here. I want to say one last sentence and then we're going to draw our thing. So one thing here is just that in this case, we weren't given, like we invented what v was going to be. We just defined it out of thin air, right? Our original equation that was given to us only had x's in it. So technically speaking, if I just said to you, solve this differential equation, since x is the only dependent variable here, your only responsibility would be to solve for x. And you should notice here that we just don't have this eigenvector component. We just get the two eigenvalues here as exponents on e, and that's it. And that's because in this particular setting, we were able to come up with a way where 1 was the x value on both of the eigenvectors right there, meaning there weren't any constant multiples for us to deal with right there. We're going to talk about when should we expect that to happen also over the course of this chapter here. So as our final thing for the day, the question is, can we draw this graph of this second order differential equation without technology? And the answer is going to be, yeah, we can. So here's the things that we know. We know that we came up with lambda 1 being negative 2. Lambda 2 is negative 5. Our eigenvector 1 was 1, negative 2. And our eigenvector 2 was 1, negative 5. And our original system, because so notice that to get a system, we have to have invented the v variable right here. But I think that this was just v and then negative 10. I don't remember what my ordering of my variables was. Negative 10x minus 7v. Okay. So from my eigenvalues, I know that they both decay. Both straight line solutions decay towards origin. So I'm going to graph my two lines based on my eigenvectors. I'm going to put arrows on them that go towards the origin because both of my eigenvalues are negative, representing exponential decay, right? That's e to the negative power. So as t gets bigger and bigger and bigger, my x value and my v value are going to get smaller and smaller and smaller towards zero, right? They're exponentially decaying towards zero. So my two lines are the straight line through the origin that passes through 1, negative 2. So 1, negative 2, I can think of, 1, negative 2 is right there. So I can think of this as like a line of slope negative 2 passing through the origin here. Okay, I did pretty good. Let me just get rid of that dot. And I'm going to call this thing V1. We also got 1, -5. So that's going to be a line of slope -5. So that's going to be the much steeper line passing through the origin here as well. That's our V2. I know that on both of these lines, I expect my straight line solutions to be decaying towards the origin. But the question is, how the heck do I fill out the rest of this graph? What does anything else look like out here? So my hint to you every time you're trying to graph something and you feel like you need more information, you should do the same smart thing every mathematician is, which is just start making stuff zero. I feel like a place where there's zero involved, where I don't know anything, is on the x-axis right here. So on the x-axis right here, I know that this is where v is equal to 0. So I'm going to ask myself, what if v is equal to 0? Let's give my hint over here. More info. What if v is equal to 0? Well, then dx dt is going to be 0, and dv dt is going to be -10x. So how does this help me? Well, this helps me by saying if we're on the x-axis, if we have that v is equal to 0, then there is no left-right motion. There is only vertical motion. So this tells me all trajectories are going to pass through the x-axis vertically. Which direction are they going? Well, I think I can just plug in a number. Notice that if x is negative, then dv dt is positive. So I will be growing up through the axis here. And notice that if x is positive, dv dt is negative. So I believe I'll be going downwards through that axis right there. So I'm anticipating for myself that I'm going to need to follow these little arrows that I know here. These are sort of like slope arrows that I now know about, little pieces of my slope field out here. But I also can tell that my two eigenvalues are suggesting that we should be decaying towards the origin from everywhere, right? This should be a sink is what it looks like 0, 0 is here. So I'm anticipating some trajectories that are going to do something like this right here. And some trajectories that are going to do something like this right here. All right. So let's go ahead and let's go as our last thing for the day. Let's go see if my kind of crappy looking picture right here agrees with what we're going to see over at Bluffton, and then we'll call it a day right here. So what I need to be able to do, now my deal over at Bluffton is I don't believe that we have a way to do, is it going to let me do one ODE? Yeah, so notice that my problem here is that it's prompting me for dy dx right here. I don't think this is going to let me do a second order differential equation at all. So notice that you don't even have a way to graph second order differential equations over at Bluffton. You have to convert them into a system of first orders first. You literally, it won't even take that in over here. So let's go back to our system over here and let's throw in the system that we found. When we were back over here, we found our system to be, oh wait, I wrote it out down here. This is what I want to be thrown in here. So I'm going to say dx dt equals, dx dt equals y, dy dt equals -10x minus 7y. This is the system that we converted out from that second order. So dx dt equals y. Get all these out of here. And then dy dt equals -10x minus 7y. Is that correct? Let me double check. -10x minus 7y. Cool, cool, cool. All right, and that's good for me right there. I'm all good with this. So let's observe a couple things. First, clearly there's some special action going on in this line right here, which looks totally to me like our maybe our -2x, our line of slope -2. Another thing I see that's really good is it does totally look like we're getting, like we said, perfectly vertical trajectories passing through the x-axis, going up and then going down over here. What I always like to do over here is double check that my straight line solutions are going to work for me here. I'm noticing that these are going in towards the origin right here. So I'm maybe going to, in fact, I think, well, Yeah, let me, it doesn't really matter. The two places that we were at 1, -2. Let's go ahead and throw that one on there. There's a straight line. That's good. I'm always going to swap my signs because I know that any constant multiple of that eigenvector is also good. That should always just get me my other part of the straight line on the other side of the origin. The other one that we were looking for was 1, 5. I think this is going to yell at me if I do a 5 since 5 is off the edge of this. So I'm going to do like a 1/2 and a 2.5, 0.5 and 2.5, right? So let's do a 0.5 and a 2.5. Oh, okay. Sorry, I forgot my negative right there, which is why that was incorrect. So let me come back to my 1, 2, 1, -2. Oh my gosh, I got to get this right here. And -1, +2. Get that one. And then I'm going to do my positive 0.5 and my negative 2.5. More straight lines. And a negative and a negative. Multiply through by a negative because all constant multiples of an eigenvector also are going to work. So we found all of our straight line solutions, and it does look like we're getting these swoopy round trajectories that are going to pass in the known direction over that x-axis, and then they're going to essentially join in with the behavior that is defined by our eigenvalues, eigenvectors. And what we're also going to see here is we're going to get a lot of solutions that are almost straight lines in between these two lines that are right here. They're definitely, and in fact, you can kind of see it. That's a curve that is kind of like it's really following in one of these rather than the other. In fact, it seems like it's following in the weaker of the two, the e to the -2t curve versus the e to the -5t curve. Again, we're going to talk about that choice of which one is it following into or away from the origin next week in next week's videos out there. But based on this graph right here, I do feel really, really good that we did appropriately graph that thing correctly. That our solutions also, by the way, we can totally go graph solutions if we so choose in Desmos. If you want to throw each of these guys into Desmos right here, we can do that. In fact, I'm going to do that right now. This is sort of my conclusion to the video if you don't care to see the Desmos stuff, but if you want to see our verification that our solution is correct, I'm going to go ahead and do that in Desmos now. So over here in Desmos, remember that whenever we plot parametric curves in Desmos, we need to give it as an x comma y statement right there. So this is always going to look like x of t, y of t is always the structure that you're going to give it to Desmos, but right now it's giving me the like warning symbol. It's like, that doesn't make any sense. So what I'm going to do is I'm going to go and I'm going to use this whole top thing as x, this whole bottom thing over here. Oh, this whole top thing is x, and the whole bottom thing down there is essentially y. We called it v, but it's y. Notice that we have parameters k1 and k2. I'm just going to call that a comma b, and that will be our initial, that'll be like a point that we can plug in right there. So let's go ahead and do this. So my x component here was my, let's see, we got a e to the -2t plus b e to the -5t. That's my first equation. Oh, sorry, pop back over here. There we go. So I got my first equation in there, and it wants me to add some sliders, and I'm definitely going to add those sliders. Now I'm going to throw in my y parts, which should be -2a e to the power of -2t minus 5b e to the power of -5t. It's got me wrapped up right there. And now it looks like, so I'm gonna always want to do something like -10 to 10, extend the bounds over which I'm looking at this guy. And now what we can do is by changing, oops, by, now by changing where our sliders are, we can get the different, ooh, looks like we're, oh man, notice that we bent through, so notice some things that I'm seeing here. One, this line is always vertical as it passes through the x-axis. By changing B, we're going to get some different, oh, always vertical through that x-axis right there. So here's all those swoops that we had identified right there that are matching the swoops that we see over here at Bluffton. So there's a swoop, and there's its matching swoops over here on the right. Here are the other swoops that we can see on the other side over here, matching their associated swoops on the left-hand side over here. So this could help me get any of my, this is my K1 and K2 for A and B right here. But just remember, in general, if you want to check if your solutions match the graphs that you're seeing at Bluffton. Bluffton's just doing our numerical method. It's not coming up with general solutions, but you can test if your general solution matches the graphs you see at Bluffton by just plugging it in parametrically into Desmos here as your x of t comma y of t, and it will produce a graph of all of those points. Occasionally you'll need to screw around with extending the time duration for some period of time, but and remember, the one thing that this doesn't do for us is it doesn't give us a direction. We really like the direction, which is why this is called a direction field. I wanted to know that this was increasing through the axis here and decreasing through the axis here. We'll lose that stuff over here at Desmos. But this at least is a good justification that the general solution that we came up with does seem to agree with the graphs that we typed in at Desmos. So I feel pretty dang good about that guy right here. So, as my closing comment then, what I just want to say is, remember, in 3.6, what we're going to do is we're actually going to more generally look at these second order equations. And so I want to argue this to you right here. It seems like you are easily capable of making the jump from that equation to this characteristic polynomial. I think that you are perfectly capable of factoring this characteristic polynomial in your head and therefore determining its roots. I think that you are perfectly capable of throwing those roots in as powers on e and stating a general equation for this. So I would like to suggest to you, you could have come up with this general solution in your head. And further, if you wanted to know the system solution, we know that all we're doing is defining our new variable v as just the derivative of the variable x. So I want to suggest to you that I truly think that literally right now, if I were to give you another one of these that at least was nicely factorable once you wrote it as a characteristic polynomial, that you could literally just tell me the x of t comma y of t or v of t solution for this thing, the general solution to the second order differential equation, literally by only doing math in your head. I honestly think that that's a reasonable expectation for me to have right there. And I feel like you should feel good about that too. And it took us a mountain of math otherwise right here. And thinking about what these diagrams are going to look like is certainly a little bit more challenging. But coming up with this general solution, once you've done enough of these, we're going to write like one less line of math every single time until we're just like stating answers. I'm going to just say to you things like, hey, is this going to have a sink or a source at the origin? And you're going to be like, sink. And you're going to be right, because we're going to be able to do a lot of this math in our heads here. So while this is challenging, and I encourage you to write out all of your work, I also want to suggest to you that you should be identifying some mathematical patterns that are happening here that should lead you to be able to maybe not show any work. And so it's going to be the case on your final exam where I'm going to say, determine the general solution to the system showing all of your eigenanalysis. It's also going to be the case in the final exam that I'm going to say something like, classify the behavior near the origin. You don't need to show literally any work. And I hope that you don't. I hope that you just sit there and stare at the corner of your ceiling for 4 seconds and say, boom, it's this one right here. I know it. And you're going to be right. So think about both ends of that. One being very elaborate here, another saying, I think I could do this in my head, and try it for yourself. I challenge you to do that. So this wraps up our straight line solutions. 3.1 and 3.2, what we covered this week, are a crazy essential basis for everything we're doing for the rest of chapter 3, which will be the basis for everything we cover for the rest of the semester. So this math matters big time right here today. All we're doing for our next 3 sections is saying, okay, how might all this play out? What are all the possible scenarios that we might see when we just do more problems that look like this right here? That's all we're covering for our next 3 sections. So they're going to be a lot of writing, but sort of a lot of repetition out here too. And you're going to see some real general themes and some real major patterns as to where numbers relate to one another, from equations to eigenvalues to general solutions to classification of the equilibria. These are all really interrelated, and the more we do of it, the more you're going to see those patterns, and it's going to become much more clear to you. So that wraps it up here today for 3.2 for me. I will see you guys for 3.3 and 3.4 next week, where we're going to say, what happens if we have real, distinct eigenvalues? What if we have complex eigenvalues? Later, we'll talk about what happens when we get repeated eigenvalues that are the same number. Or what happens when one of our eigenvalues is 0. That's going to give us a little bit of odd behavior out there as well. So that's when we're going to get into sort of our special case scenarios that we're going to end up seeing out there. So next week is real, distinct. That's a word that I didn't throw in up there. And complex eigenvalues are 2 sections that we'll cover next week. I'll see you guys for those. Have a good one, everybody.